Okay, good afternoon, everyone. Welcome to my talk about 5G wireless systems. Here is the outline of my presentation. I will start with shortly introducing myself and the company where I work for, and then I would like to take you on the road through 5G. I will start with what are these requirements now, and I would like to walk you towards the specifications. How do we get from the specifications towards the system, towards the circuits, and then in the end, what do we measure, and a short conclusion. So first of all, who am I? My full name is Elly de Pelecijn. I did a PhD here in Belgium at KU Leuven, where I worked together with Professor Steyaert on fully integrated high voltage power conversion. Afterwards, I decided it was time to switch topics, and I went to work for Huawei, where I did RF and millimeter wave design. And recently, I switched to ICANN, where I'm still working as an RF designer. So where do I work? ICANN is a very nice and small company with a fabulous semiconductor component supplier. We are actually part of the big Foxconn group, where about 1.3 million people are working for. We mainly make products for the wireless telecommunication market, and our products can be split in two main parts, which are the sub-6 GHz components, where you find a lot of amplifiers, attenuators, and so on, but also the millimeter wave applications, where I will show you today the beamforming IC. And then we also have different kind of front-end modules where we cover the frequencies for 5G. Now let's have a look at 5G systems, and we will start with a very short history class. It will only take me one slide, so don't worry. But communication started about the early 1900s with the invention of the telephone and then the radio. Nowadays, we talk about mobile communication, and we talk about the X generation. And I will shortly show you some aspects of the different generations that we have. So first of all, in the 1980s, we started with 1G, where everything was still analog, the decoding, and we could transmit some voice calls, but they were often of very poor quality. And you see that the frequencies we used were strong below 1 gigahertz. Then afterwards, in the second generation, the SMS, our text messages were added, and the quality of our communication went already up. Everything became a bit cheaper, and we were close to these carrier frequencies or even above 1 gigahertz. And then with the third generation, we all probably still know it. There is the mobile internet that came by, and a lot of faster data communication with frequencies around 2 gigahertz. Then 4G in 2010, approximately. There a lot of features were added to everything. So we have real-time video, high-speed videos, very large data rates, lower latencies, and you see that with the generations going up, also these carrier frequencies where we are working at are going up. And then nowadays, we call it 5G. That's what we all are mostly using nowadays. And what they generally say is we have a better operational performance. Now, I will talk about this a bit later in the slides, but now still we see also this grayed out 6G. This is coming. We don't know when, we don't know what it is exactly, but it's coming. So a bit more about 5G and what I mean with we want a better performance. So in some previous slides of my colleagues, you already saw this ETSI. What you also can see a lot is GPP. These are instances who set actually what we want from requirements and what are the surroundings of how our communication is working. And from these instances, I have this nice graph where actually 4G and 5G are compared. 4G is in the light blue in the middle, and 5G is in the darker blue. And mainly what you see is we want to do better on all aspects. We want a higher data rate, we want a higher efficiency, we want more mobility, a lower latency, and so on. And these are actually the most important requirements for our mobile communication. In the meantime, we also want a higher efficiency, so power efficiency, a higher reliability, and if we combine all these aspects, yeah, that's a big trade-off in our systems, and it also has a large impact on the bandwidth and the circuits that we are making. Now I will try to explain a bit more about 3 of these topics, because they will come back in the remainder of this presentation. So first of all, the data rate. The data rate, probably you all know, is a speed at which our data is transmitted or received. It's measured in bits per second. And some typical examples are shown on the slide, which are a phone call, which uses about 64 kilobits per second. For a video call, we are around 1 to 2 megabit per second, and for a HD video, it's about 5 to 20 megabit per second. And what we want to achieve, based on the requirements for 5G, is peak data rates up to 20 gigabit per second. This is 20 times more than what was possible with 4G. But be careful here, there is clearly written peak, so it means all the data that is sent through, and this contains your information as well as your error correcting codes and so on. Then the next one, I found in a nice one for an example, is the area traffic capacity. It's the total throughput that we have through a geographical area, and it's measured in megabit per second per square meter. So what you can imagine is, imagine a square meter and how much data we can send through that square meter. In 5G, we want to improve this with a factor of 100 and go to 10 megabit per second per square meter. Now, these are all numbers, and it's probably hard to imagine this. So that's why I made an example. So if we take our video call, it was about 1 megabit per second that we need for one person. For 4G, one person, so each one of you, would need about 10 square meters. Now, when we go to 5G and we upgrade, then it means that in this 1 square meter, 10 people could have a video call at the same time. At this moment, I think this data rate of 10 megabit per second isn't the issue anymore, but 10 person per square meter will get more difficult to achieve. And then we still have the latency, which is also a very important one for 5G. We want the latency, which is the delay that we have in our communication network, to go down with a factor of 10, and it's about 1 millisecond that we want to achieve. Now we have all these specifications or requirements that we want, and that people say, okay, I want to achieve this. The next thing is, how do we achieve this with our design, and how do we translate this into specifications for our systems? I will start with the higher frequencies. As you saw in the historical overview, we are always going to higher carrier frequencies. And the reason for that is that we need higher bandwidth. And this is actually a bit dictated by the equation of Shannon, where he says that the capacity that we can transmit, which is basically our data rate we can get through a channel, it depends on the bandwidth, here the W, so the frequencies in which we can transmit our data, the number of antennas that we use, and a function of the SNR. Now, mainly on this end, yeah, we can improve it. We can use beamforming and so on. And this SNR, there we are more or less stuck. So where we should play at is this bandwidth. This bandwidth should be increased, and this is only available at higher frequencies. Because, for example, if we want to go to a bandwidth of 500 megahertz, you cannot do it at 200 megahertz because it's just not there. You need to go to these higher frequencies. And that's why for 5G we defined 3 bands in the 24 to 40 gigahertz range with a bandwidth of 100 megahertz to 1 gigahertz. And on this following slide, I just quickly draw the idea of Shannon's theory. The left part is a quick drawing of how this would, what this would mean in your capacity versus SNR when we normalize it to the bandwidth. But more interestingly is probably the right side of this slide, where you can see that if we go higher in the bandwidth that we can use, that we can get much more capacity, and that we definitely need this if we want to go to this 10 gigabits per second. Now, to go to the next translation of system specifications, I do a very short recapitulation of what is a modulation scheme. Very simplistic, we can have ones and zeros. We can turn our signals on or off or give it another amplitude, and then we can send data. Now, what we can also do is use a symbol with different amplitudes or different phases and therefore contain more information in that one symbol. And that we typically represent by a constellation. And I took the 16 QAM as an example over here. So here we have 16 different possibilities. And due to a difference in amplitude or the phase based on the rotation, we can get different symbols. Now at the receiver, we will not get exactly these points. What we will receive is what they call these clouds around the points. You will have your desired point, but you will sometimes receive a bit off due to a change in amplitude, a change in phase, and so on. And to characterize the fact that we are sometimes off, we use the error vector magnitude. Now, this error vector is actually a vector that we can draw from the point that we want to the point that we receive. And by taking then a normalized root mean square of all these vectors, we try to summarize all these different vectors in one number, which is the error vector magnitude. And this I will come back on in the next slides. So next, we already translated that we need a higher bandwidth, but what other system specifications can we decide on? First of all, what we often do in design for millimeter wave is we go to our system engineer and we ask for a bit error rate. This is an error rate that our system can tolerate. And if we do some complex math, which is written in this nice paper, then we can calculate the SNR for the system. I will show you this on the graph. So for example, if we take the 16 QAM line over here, where we had our 16 symbols, and for example, if you can tolerate 10 to the minus 3 in bit error rate, then we would need around 15 to 20 dB in SNR. So that's the next system specification that we can use. Now you can also translate in the same way with the same kind of equations towards an error vector magnitude, which is also a spec for the system that we can use. And then, how do we define now? Typically, we have a receiver, we have a transmitter. How do we define which one gets so much SNR and the other how much the remaining part? That's typically 50-50. But in general, if you want to divide it otherwise, you need to make sure that this equation is holding. And that brings me to a design. So we have now some specifications for the system. Let's now go to the design. This is a design that we made at ICANN. It's the beamforming, as we call it. On top, you have the receiver chain. At the bottom, you have the transmitter chain. And then here you have a lot of phase elements for the beamforming, actually. And then we go through the RX, so I will quickly go through all the elements and important aspects. I will not go into depth of all these circuits because there are many of it, but at least then you have a notice on what's important and where should we look at if we want to design such a system. So if we look to the RX, we typically first have the LNA, the low noise amplifier, and then you will see different VGAs and DSAs, which are variable gain amplifiers and digital step attenuators. Now, if we start from our system spec, we have an SNR for this RX chain. And what you can typically do is do a calculation for the whole chain. You can calculate the noise figure or the SNR. But in receiver systems, this LNA is the most important one for the SNR. So the SNR will be dominated by the LNA, and that's where you need to design this for. Other elements in the design of our RX are, of course, our input matching, because we want to receive all the information from the antenna. So we need to make sure that we are matched towards our antenna. Then we will add this variable gain in these blocks with these VGAs and DSAs. This is so that we can have an optimal design for noise or linearity. But what we can also do with it is we can adjust our gain depending on the temperature. So you can actually calibrate so that it works properly. And then, of course, we always have a trade-off. There is here a trade-off between the noise matching and the power matching. Then next is a TX site. At the TX, we see again these VGAs and DSAs, but probably the most important block is the PA, the power amplifier, which sends all the power towards the antenna. Again, for this chain, you will be able to determine an SNR or an EVM, and this is dominated by the PA. Another thing that is dominated by the PA is the total power that you can deliver to your antenna, and which is mainly set in an output compression point. And this leads to a trade-off again. Because what we typically want is impedance matching, that's what you learn in class, is to have a conjugate match. But on the other hand, we want also a certain power to be delivered, and therefore we need a power match. And if we would plot this on a Smith chart, we could plot two different regions, and you see that, for example, the region where a power match and the region where we have a conjugate match don't match. So there is a trade-off in what we actually want. So now we have our design. Next step is not immediately the measurements, but how do we get from the design to the measurements and beyond? So as you will see in RF design, you will probably cycle a lot of times through what I show here. So you have the schematic, and from your schematic you go to your layout, and afterwards you do some verification. But based on this, you will see, okay, maybe this or this is not working fine, so you will need to go back to your schematic and back to your layout. And this you will do multiple times to get your circuit right. What is also important is that you communicate with the system engineers or with the guys doing a top-level simulation with all the blocks together, because your system needs also to be verified, and how your block, for example, work needs to be verified by the system. And then some very important elements if you do the layout for a millimeter wave. It's very important to evaluate everything carefully, because parasitic elements can shift everything, your performance, it can deteriorate everything. And I try to explain this with a small graph. I quickly drew it by hand just to illustrate that we can have a certain gain in a system versus frequency. I didn't put numbers on it, but just suppose it's some kind in dB and something in the gigahertz, and this is the gain that we simulated with our circuit. Now, if we then extract the parasitics from our layout, we get this curve, for example. This is maybe with a bad design, but what you see, what can happen is that our frequency, it shifts down. So every frequency is shifted down. Also, our gain is shifted down. And what can also happen is that your bandwidth also changes. So a lot can go wrong if you don't do your layout right. So that's very important. And one important element there is to use symmetry, symmetry, symmetry. It's something I learned from my supervisor, Michiel Steyaert. If your design is not symmetrical, then probably your design is not done very well. Now, how do we take this into account? What we use are some tools. First of all, a parasitic extraction, where we can extract the resistance and capacitances in our circuit. We do also EM simulations from the inductive elements in our circuits or in the transformers and so on. And what we afterwards do, once we have these and once our circuits are tweaked a bit, we can do also some modeling, because if we use parasitic extraction models or EM models in our simulation, everything becomes much slower. So we do a modeling that represents all these elements, and everything can be faster. Now, okay, the layout needs to match the specifications, and you also know the DRC, LVS, that needs to be fine. But what is also important is, for example, EMIR. When you draw a line, you need to be sure that the current that you want to go through that line can go through it without breaking it. So that's an extra step that you need to take. You also need to take into account corners. Based on where your chip is on the die, it can vary in how it's working, so that needs to be taken into account at design time. And always take into account the system, because between the blocks it's important to match. It's also important to not break the chain and meet the overall specifications. And then once the design is done, you go to a chip. you would go to a tape out, and first you get this bare die back. And then afterwards, what we do is we package them. So we package them to protect them and to have the fan out towards the board, as you can see over here. This is the chip that I showed you the system before, so the beamforming IC, operating at 28 gigahertz. And then afterwards, what we do is measurements. As you can see over here, in blue is, for example, the gain of the RX and the TX. You also see the noise figure in the red curve. And then on the right, an example, as I showed you before, from a constellation that we measure. You see these typical clouds of data points. And one thing I want to let you know is it's okay to make mistakes. For example, there can be a mistake in your measurements or if you made your product, but you will only make it better if you learn to understand then the problem and to make your product better afterwards. And then, of course, what's next? Next, we want to go for a product. And for a product, as already many colleagues told you before, it's important to collaborate. We need different teams to work together. We have our analog or RF design team, but the digital team is also very, very important. We have a packaging team, test team, manufacturing team, and so on, where we all look together to design for testability and manufacturability. So, and that brings me to the conclusion of my talk. So I tried to guide you through the idea of a 5G system, so from system specification to a product. In 5G, everything needs to be faster, and we want to connect everyone, everywhere, all the time. The requirements can first be translated into system specifications and afterwards in block specifications. And it's very important to take the layout into account at these millimeter wave circuits. And then once the chip is packaged, it's time to measure, learn from the results, and make a product out of it. Thank you for your attention.